Right, so for our next wee unit of work, we need to do some work on describing large and small numbers using prefixes and scientific notation. For the electromagnetic spectrum, that everything in the electromagnetic spectrum travels at the speed of light, which is a crazily large number of 300 million metres per second. So in physics we use prefixes and scientific notation to describe large and small numbers and make dealing with them, processing them and performing calculations nice and straightforward and easy. So we've got our prefixes first of all. In that 5 we use everything from nano to giga, from smallest to largest. So starting with the smallest, we've got nano. Nano is 1,000th of a million, which is 1 times 10 to the minus 9. Really small number used to describe very small things. Next we have micro. Micro is 1,000,000th. So a microsecond would be 1,000,000th of a second, a really short measurement of time, times 10 to the minus 6. Then we have milli. Milli you should be familiar with. The millimetre, really short measurement of length, and there's 1,000 millimetres in a full metre, so 1,000th of a metre. So that's your small ones, nano, micro and milli. Then we can use the same but for large numbers. So kilo, again you should be familiar with. A kilometre is 1,000 metres, so the prefix kilo is 1,000 or 1 times 10 to the 3 zeros onto the end of your number. Mega is 1,000,000, like a megabit in computing or internet speed. Megabits per second, so that's 1,000,000 or times 10 to the 6 zeros. And then we have 1,000 million, which is giga. Giga is times 10 to the 9, so that's 9 zeros onto your number, 1,000 million. So that's your prefixes. We use them throughout the National 5 course and beyond. So electromagnetic radiation, all electromagnetic waves, that's radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays, they all travel at that ridiculous speed, 3 times 10 to the 8 metres per second. And SQA quote it as 3.0 times 10 to the 8 metres per second, quoted to 2 significant figures. SQA are obsessed with significant figures, and we need to be careful with our use of those as well. So 300 million metres per second, that's the speed of light, 3 times 10 to the 8. So significant figures, we should be rounding all of our answers to the fewest number of significant figures, which is usually 2 or 3. That's why the speed of light was quoted as 3.0 times 10 to the 8 metres per second. That's SQA telling us if you get an answer with a big string of numbers, round it to 2 significant figures, since the speed's given to 2 significant figures as well. So we can use those to answer questions questions 15 and 16 in our homework questions. So question 15, the speed was given as the speed of infrared waves. It's a question about infrared because it's about a remote control. So it says remote controls use infrared signals. Calculate how long it takes for a signal sent from a remote control to arrive at a sensor on a TV which is 3 metres away. So it's a speed, distance, time calculation. So laying the working out, laying the numbers out before we do the calculation. The question doesn't tell us what the speed is, but it does tell us that it's infrared signals, and infrared waves are part of the electromagnetic spectrum, so they travel at 3 times 10 to the 8 metres per second. They're travelling a distance of 3 metres, and we need to work out how long it takes or the time taken. So we've got everything we need there. We've got 2 values for speed and distance, and we're using that to calculate our unknown time. So distance equals speed times time's our formula. Rearranging that to get time on its own, that will be distance. Take the v over to the other side, so the v becomes divided, so it becomes d divided by v. So the time is the distance divided by the speed, just using our simple change side, change sign rule. Subbing the numbers in, that's 3 for the distance, divided by 3 times 10 to the 8 for the speed, and that's going to come out to a ridiculously small time. Now we expect it to be a small time because it's covering only 3 metres while travelling at 300 million metres per second. That's how ridiculous light is. It travels 300 million metres every second. So let's just try that on a scientific calculator. Casio scientific calculator here. Very good scientific calculator, reasonably priced as well. I don't work or collect royalties from Casio, but I do recommend it. 3, divided by 3, and then the 3 times 10 to the 8, this button down here, just below, next to the answers and the equals, that's your scientific notation button, and you just do 3, then the magic button, and then 8, so that will do 3 divided by 3 times 10 to the 8 for us, and that comes to 1 times 10 to the minus 8 seconds. So that's 1 times 10 to the minus 8, and then the unit seconds for our answer. That's question 15. Should come to 1 times 10 to the minus 8 seconds. Try it yourselves. Question 16 was using the VF lambda formula. It said that there was a frequency of radio station of 94.3 megahertz, and calculate the wavelength. So again, the question doesn't tell us what the speed is, but we know that because it's a radio signal, don't get the radio signals confused with the sound that comes out of radios that we listen to. Radio signals are electromagnetic radiation. They're used to transmit not just radio signals, but satellite TV, wireless internet, communications to and from satellites, all make use of radio waves, and radio waves are part of the electromagnetic spectrum, travelling at 3 times 10 to the 8 meters per second. The sound that comes out of our radios that we hear the music from, that's obviously sound from a loudspeaker, and that's the speed that travels at the speed of sound. Our ears pick up that sound, and that's where we use 340 like we did in the last set of questions. But when it's a radio signal, it's electromagnetic spectrum, so it's 3 times 10 to the 8. The other thing here is the frequency was given in megahertz. So mega, remember, is 1,000,000, 6 zeros. So 94.3 megahertz is 94.3 times 10 to the 6 hertz. So there's quite a lot involved in that. We have to select the speed of the radio signals, is 3 times 10 to the 8, and we have to use the prefix, the times 10 to the 6, to get the correct frequency, all before we use our formula to work out the wavelength. So it's V, F and lambda, that's our wave equation, V equals F times lambda, and more processing needed here. We now have to rearrange that, get lambda on its own, so lambda times F equals V, so we want lambda on its own, we have to take the F over and divide through, so V divided by F is equal to lambda, giving us lambda equals V divided by F. We rearrange in triangle that people like, V on top, F and lambda. You don't have to do this, but some people like it as a wee visual. So lambda equals V divided by F. V equals F times lambda, and F equals V over lambda. Subbing the numbers in, lambda equals 3 times 10 to the 8 divided by 94.3, and we need the prefix converted, times 10 to the 6 because it was megahertz. Now that should come to 3.2 meters, to 2 significant figures. Let's try it in the calculator. So 3, magic button 8 to give us the 3 times 10 to the 8, divided by 94.3, magic button times 10 to the 6. So that's how it goes in your calculator. 3, then the scientific notation button 3, magic button 8, divided by 94.3, magic button 6. That comes to that as a fraction. Use that button there to convert it to a decimal, and then it's 3.181336161. Now we don't leave it as a big string of numbers. SQA are obsessed with significant figures. The fewest number of significant figures there is in the 3.0 times 10 to the 8. 94.3 is given us 3 significant figures, but just 2, we use the fewest. So that should be to 2 significant figures from the fewest number of values used in the question. So that would round to 3.2. The 1/8 would round up to 0.2, so it's 3.2 meters. Okay, so a wee bit more numeracy required, but at National 5 it's really not getting much more difficult than that. It's using our equations, being able to rearrange them, and then dealing with prefixes when necessary, and making use of scientific notation and rounding our values to a suitable number of significant figures. So I hope that helps.